In section 1.5, we'll focus on expressing infinite solution sets in parametric vector form. In doing that, you'll get to practice linking algebra and geometry of systems of equations and their solutions, linking matrix equations, vector equations, and systems of equations, classifying linear systems as homogeneous or non-homogeneous, and characterizing linear combinations of vectors and the span of a set of vectors, both algebraically and geometrically. In our first example, suppose that the augmented matrix for a homogeneous system AX equals 0 reduces to the following. Write the solution set in parametric form. And that's something that you've seen already. So take a second and try to write that solution yourself. From the bottom row of the matrix, I can see that x3 is equal to 0. And the x2 column in the augmented matrix doesn't have a pivot. And so that means that x2 is free. I'll assign x2 to be equal to t. The top row of the matrix tells me that x1 minus 2x2 plus 2x3 is equal to 0. Solving that for x1 tells me that x1 is equal to 2x2 minus 2x3. And then substituting x2 equals t and x3 equals 0 into that equation gives me that x1 is equal to 2t. So I have the solution x1, x2, x3 is equal to 2t, t0. And that's the parametric solution. A way of making this simpler to interpret geometrically is to factor that t out. If I factor the t out, I've written the same solution, x1, x2, x3 is t times the vector 2, 1, 0. But now it seems obvious that x1, x2, x3 are all of the multiples of 2, 1, 0. So our solution set is the line that's spanned by the vector 2, 1, 0. We call that factored form for the parametric solution, the parametric vector form. And again, geometrically, the solution space is a line through the origin and is defined by that parametric vector equation, all of the multiples of the vector 2, 1, 0. And another way of thinking about that is the span of the vector 2, 1, 0. Thinking about homogeneous equations in general, so systems of the form AX equals 0 in general, we know that x equals 0, which we call the trivial solution, is always a solution to AX equals 0. Think about what the matrix vector product AX is. It's taking the linear combination of the columns of A using the entries of X as weights. So if every entry of X is 0, that means that all of the weights in our linear combination are 0. And so the linear combination itself is 0. So x equals 0 is always a solution to AX equals 0, and that's why we call it the trivial solution. If any variables are free, then we have non-trivial solutions, so non-zero solutions to AX equals 0. If we have one free variable, then our parametric solution would be of the form t times some particular vector. In the language of span, that's the span of that vector, and geometrically, that's a line through the origin. If we have two free variables, then our parametric solution is a linear combination of two particular vectors that are not multiples of each other. In the language of span, that's the span of those two vectors. And geometrically, that's a plane through the origin. We can build off what we understood for homogeneous equations to understand non-homogeneous equations. So in this example, we're looking at an augmented matrix for the system AX equals B, where B is not the 0 vector. And we know that it reduces to the given matrix. We want to express the solution set in parametric vector form. So first, just find the solution set. So express the solution set in parametric form, but you don't need to worry about factoring things and writing it in parametric vector form. This is the solution that I found. And the way that I went about finding it is that the bottom row told me that z was equal to 1. I could tell that y was free, so y was equal to t. And then the top row told me that x minus 2y was equal to 1. So solving that for x, I knew that x was equal to 1 plus 2y, but then y was equal to t. So there's my parametric solution. Now to write it in terms of a parametric vector solution. So looking at those components for my xyz vector, I see that they're composed of two different types of things. They're constant terms and multiples of t. So that means that I want to write every entry in that vector as some constant term plus some multiple of t. So rewriting the x term, I don't have to do anything because it was already 1 plus 2t. Thinking about y, another way to write that is 0 plus 1t. And thinking about z, another way to write that is 1 plus 0t. And now I can write the vector 1, 0, 1 and add t times the vector 2, 1, 0. So I'm able to find my parametric vector form because I wrote everything as a constant plus a multiple of t. So t times the vector 2, 1, 0 is the solution to the homogeneous system if b were equal to 0. We actually just saw that in example 1. And 1, 0, 1, that's a particular solution to the non-homogeneous system. If we let t be 0, then our solution would be 1, 0, 1. So if I plug x equals 1, y equals 0, z equals 1 into both of the equations represented in the system, they would satisfy both equations. The solution to the non-homogeneous system is just the solution to the homogeneous system shifted by the particular solution. Looking at another example, suppose the augmented matrix for a system reduces to the following. Describe the solutions geometrically and in parametric form. Translating back to equations, the top equation tells me x minus 4y plus 5z is equal to 6. And then the y variable was free, so I'll let y be equal to s. And the z variable was also free, so I'll let z be equal to t. Then substituting y equals s, z equals t into the top equation and solving for x gives me this parametric solution. And now I'm going to write it in parametric vector form. So I can see that I have constant terms, multiples of s, and multiples of t involved in my solution. So I need to write every entry in that vector as a constant term plus a multiple of s plus a multiple of t. The x is already written that way. For y, that's 0 plus 1s plus 0t. And for z, that's 0 plus 0s plus 1t. And now I can find my constant vector, my vector that s multiplies, and my vector that t multiplies. So I know that the parametric vector solution is the vector 6, 0, 0 plus s times the vector 4, 1, 0 plus t times the vector negative 5, 0, 1. And that really cool geometry applies here as well. The gray highlighted piece is the solution to the homogeneous system. If the right-hand side had been all 0, we would get that plane for our solution set. And then I take that plane and I shift it by adding 6, in this case, to each of the x coordinates. And that gives me the solution to the non-homogeneous system that I was presented with. So I take a particular solution and I add it to the homogeneous solution to give me the overall solution to the non-homogeneous system. And here's a picture. So the gray plane is the solution to the homogeneous system, and the blue plane is the solution to this non-homogeneous system. In our last example, I wanted to help you get more comfortable with writing solutions in parametric vector form. So I tried to come up with a big example. So express the solution set to the homogeneous system with the given coefficient matrix. Well, the first step would be to find the row echelon form of the matrix and then analyze it to come up with a parametric solution, and then we can write it in parametric vector form. So here I've used Maple to find the reduced row echelon form for the homogeneous system. I can tell that I have 3 pivots, x1, x3, and x5 contribute pivot columns. So then I have 3 free variables, x2, x4, and x6 are all free. So next, I'm going to translate the information into a series of equations, and I'm going to try to be pretty efficient about it. So looking at the x1 variable, that has a pivot. So the row that contains the pivot, I'm going to translate that as an equation. x1 minus 4x2 plus 5x6 equals 0. Then in the next row, I'll think about the next variable, x2. x2 is free, so I'll assign it a parameter, x2 equals t. Then the next variable to think about is x3. x3 has a pivot, so I'll translate the row that that pivot is in into an equation. That says that x3 minus x6 is equal to 0. Then moving on to x4, x4 is free, so x4 is equal to s. Thinking about x5, the column for x5 has a pivot. So I'm going to take the row for x5 and translate it as an equation. x5 minus 4x6 is equal to 0. And finally, x6 is free, so I'll write x6 is equal to parameter. I wrote x6 is equal to w. Then solving for the variables and substituting when appropriate, I can see that x1 is 4t minus 5w, x2 is t, x3 is w, x4 is s, x5 is 4w, and x6 is w. Now I need to re-express things so that I have enough information to pull out the parameters and get the vectors that I need in my vector parametric form. So I can see from the middle column that I have t, w, and s variables, and I don't have any constants because I have a homogeneous system. So I'm going to need to express every single variable as something times t plus something times s plus something times w. So looking at x1, that's 4t plus 0s minus 5w. x2 is 1t plus 0s plus 0w. x3 is 0t plus 0s plus 1w. x4 is 0t plus 1s plus 0w. x5 is 0t plus 0s plus 4w. And x6 is 0t plus 0s plus 1w. And I've copied that information onto this slide. So now just factoring out the t, the s, and the w gives us our parametric vector solution. So the vector x1, x2, x3, x4, x5, x6 is t times the vector 4, 1, 0, 0, 0 plus s times the vector 0, 0, 0, 1, 0, 0 plus w times the vector -5, 0, 1, 0, 4, 1. And those three vectors that I just read off, they span the space that is the solution set to this homogeneous system. It's a three-dimensional space in R6. And I had told you that example 4 was the last example, but I lied. I did have one more example. I'm sorry. So here we're thinking about the same coefficient matrix, but now instead of looking at a homogeneous system, we're looking at a non-homogeneous system, ax equals b with this particular vector b. And we are again looking for the solution set in parametric vector form. So again, I'll do my row reduction. And of course, a row reduces to the same thing. And now I have a right-hand side that was all zeros before. Going through the exact same process that we went through before, we can find out the parametric vector solution. But now we'll have constants in those expressions for x1, x2, x3, x4, and x5 as well. And that leads to the blue shaded vector. I think it's pretty cool to think about, well, that 3, 0, 1, 0, negative 3, 0 is just the particular solution to the system of linear equations. And then the gray part is the homogeneous solution if b were equal to 0. And actually, you can read off the particular solution just by looking at this row reduced echelon form. If we let all of the free variables be equal to 0, so you can see x2 is 0, x4 is 0, and x6 is 0, then the first row would tell me that x1 is 3 because x2 is 0 and x6 is 0. The second row would tell me that x3 is 1 because x6 is 0. And the third row would tell me that x5 is -3 because x6 is 0. And so I get that blue highlighted vector. So I actually didn't have to go about solving the system in parametric vector form again. I could use what I knew about the homogeneous system and just add on the one particular solution when all of my free variables were 0 to get my overall solution for the non-homogeneous system. Of course, I could have redone everything and I would get the same exact answer. So one thing that I wanted to point out is these parametric solutions are not unique. You could get a parametric, you could go through a process and get a parametric solution, and I could go through the process and get a parametric solution, and our parametric solutions might not be the same, but they would describe the same space. If we were to graph our solution sets, they would describe exactly the same space. So now you've finished watching the video. You are ready to read section 1.5 in your textbook and try the practice quiz.